Today is June 25th, 2025, and I am Hansen Hsu here with our second session with Jürgen Schmidhuber. And I want to start with a couple of questions that I didn't get to ask yesterday.
Hmm.
Um, First is um, in today's world of AI. Transformers have seemingly mostly replaced LSTMs for most natural language tasks, and things like machine translation, things of that sort. Is there still a place for LSTMs today?
I think that's an interesting question, and the answer is yes, of course, because LSTMs are really efficient compared to the modern quadratic transformers. Why that? Because they scale linearly, which means if you have 100 times more text, you need 100 times more compute. And with the quadratic transformers of today, if you have 100 times more text, you need 10,000 times more compute. So it scales quadratically. And as we already discussed the other day, um, why is that feasible at all? Mainly because compute has gotten so cheap through these GPUs, the graphic processing units that mostly NVIDIA is producing and that everybody's now using in huge data centers to deal with long texts. Interestingly, I think also mentioned yesterday, the linear transformer, there's a linear version of the transformer, goes back to 1991 when there was a transformer variant, which just like today's modern quadratic transformer, also learns to generate these keys and the values, and then generates a mapping, an attention mapping, as it is now called, which then is applied to queries such that through gradient descent, the whole system can learn to optimize some error function, to minimize some error function, by inventing good keys and good values at the right moments in time to process the data that is coming in. All right. And now, with a recurrent network like LSTM, the linear scaling is obvious. So that's the nature of these recurrent neural networks. And interestingly, in principle, these recurrent networks are more powerful than uh, any kind of transformer. Why? Because of these recurrent connections, which allow them to basically implement any program that can be implemented on a standard computer. So, for example, you can learn on recurrent neural networks with an LSTM, for example. You can learn something that is called context context-free languages, where you normally, with a standard computer, need something like a stack. For example, the simplest context-free language is A and B N. What does it mean? It means if you have 5 A's in a row and then you have 5 B's in a row, then that's a legal example of the language. But if you have 6 A's in a row and then you have 7 B's in a row, then it's not symmetric. So you have an illegal example um, of this language. And then more complicated things, which are called context-sensitive grammars, where you need a more complicated traditional device to implement that. And now recurrent networks, ignoring storage limitations, they can learn to implement all of that because they are general purpose computers. And LSTM, for example, finds it really, really easy within a few training examples to learn certain context-free grammars and context-sensitive grammars. And transformers find that completely hard. It's very difficult for them because basically they are feed-forward networks, And and only if you give them feedback such that they also become recurrent networks, only then you can make them more general. But the transformer per se is quite a limited device, so it's not as general as a recurrent network. And it turns out that certain trivial tasks, such as parity, which is just you have a sequence of ones and zeros, 0, 1, 1, 1, 0, 0, 0, and then you want to give that as an input to a neural network, and it should say yes if the number of on bits in the input string is odd, and otherwise it should say 1. So it is basically classifying the numbers of on digits, of 1 digits, as to whether they are odd or even in that example. So it's a trivial thing, and for a human, it's really difficult for a transformer to learn stuff like that, for a traditional transformer. And then a recurrent network finds it trivial to learn that. For example, you can take a little tiny recurrent network and you just feed the input one by one, so 1, 0, 1, 1, 1, and it has just one single hidden unit, and a connection to itself, and it has a few other connections, but maybe only 5 connections in total. And then you can use the most stupid learning algorithm of all time to train that recurrent network. The most stupid learning algorithm of all time is this: just randomly initialize all these connections, all the weights on the connections between -10 and 10, and check, does it work? Does it work on 3 training examples? One input string of length 5, another one of length 10, and another one of length 17. Now, in 1 out of 1,000 random cases like that, it will be able to classify these 3 examples, and it will generalize to all the unseen examples as well. Why? Because the recurrent network has discovered the very simple algorithm which you need to solve the parity problem. It has learned to implement a flip-flop. Because all you need to do is whenever new 1 comes in your input, you just have to flip the internal state, and then at the next one, you flip it again. And so you basically can, just through these flipping operations, decide whether the number of 1s that you have seen so far is odd or even. So it's something that a recurrent network can do trivially, without even gradient descent, just random weight initialization until for the first time it works in a training set. And then you can be pretty sure that it generalizes to all kinds of long sequences outside of your tiny training set. So recurrent networks in many ways are much more powerful, theoretically more powerful than transformers. However, the modern quadratic transformers work really well on natural language, where you have imperfect language like the one that I'm producing now, where I have all kinds of m's and o's, and I repeat stuff and I do all kinds of things that you shouldn't do in perfect English language in writing for a novel or something like that. And then it turns out that it can deal with that really well. But all of that just shows that natural language is much easier than what linguists of the previous century thought, the linguists who talked about context-free languages and context-sensitive languages. No, natural language in many ways is really simple. It's so simple that a feed-forward network, such as a transformer, can solve it. So it just shows that some of the problems that have been considered difficult for a long time aren't really so difficult. You just need enough parameters and a huge network and enough compute, and then suddenly it can talk as well as a human. Let me say, as a human politician. So transformers are pretty good at talking in a convincing way, like politicians, and what do? They always say maybe more or less the same thing that they have said already 100 times in previous speeches, and always getting the basic message across, always taking the context into account. So if you are talking in this city, you will deliver your messages in a slightly different way than when you're talking in a different city with a different kind of population and so on. But you always say more or less the same thing. And the transformers and feed-forward networks like that, they are really good at doing that as well. And they sound convincing, like politicians tend to sound convincing. They're not so good at thinking around corners, like mathematicians do, or like little flip-flops do. Flip-flops also think around corners because they basically compute a knot of a knot of a knot through a recurrent or recursive operation of a simple kind. So they think around corners. Humans, in general, find it different. No, humans find it difficult to deal with not, and realize, oh, that means the same as nothing. And mathematicians and logic programmers, they find all of that easy. And theorem proving, where you have to think around corners, all of that is easy for a traditional symbolic system and for a recurrent network. And it's not easy for something that's good at natural language processing, such as a transformer, which is one of the reasons why as soon as you come to mathematical problems, you need all kinds of additional tricks to make transformers work.
Wow, fascinating. Thank you for that. Um, so I guess a related question is uh, recurrent neural networks. So I guess one of the big things about the Transformers paper is that it focused everything on attention, but attention wasn't itself wasn't new, right? Like recurrent neural networks already used a form of attention, or is that correct?
Yeah. So, for a long time, the large language models were basically LSTMs. So you had an input LSTM taking in something, some text, and then an output LSTM taking the internal representation generated by the LSTM and transforming that into an output string, an output sentence, an answer. And so that's how you could build chatbots such as Tay. There was a chatbot by Microsoft called Tay, and 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 actually it was a disaster because they first had it in China, and then the Chinese they spoke politely to it and it did nice things. But then when they rolled it out in the Western world, some of the guys they realized, oh, you can train it to become a Nazi by just giving them lots of Nazi slogans and whatever, and so they had to take it off, had to take it, had to delete it. But so basically, there was this time when there were these two recurrent networks, the LSTMs, doing the language processing. Then there was some intermediate period where there was an additional way of introducing attention to certain parts that happened in the past. And all of that goes actually a long way back, because in 1991, there was already this attention mapping. In 1993, I even called it um, learning internal spotlights of attention. So that was a generalization of the unnormalized linear transformer, which was published in 1991, and then in neural computation in 1992, and then in 1993 I had this this extension where the whole network was not just a slow feed-forward network manipulating, learning to manipulate another fast network, both of them feed-forward networks. No, suddenly everything was recurrent, such that it was more general. And then I said, okay, now what this network is basically learning, it's learning internal spotlights of attention. So the attention terminology also goes back more than 30 years. Now we have 2025, so that was almost a third of a century ago. So the need for attention is an old hat. Yeah.
Thank you. Um, and yesterday you also mentioned that like today's LLMs, going back to 1991, a lot of your work then was already using self-supervised pre-training. And
Yeah.
so it's interesting that not just your work, but also the rest of the field kind of moved away from pre-training to pure supervised learning, and then
That's
pre-training has come back. So, sort of, why is that?
That's true. Yeah, it's true. It's cool that you know that. Oh, so many people have no idea about that, but it's really true. So in 1991, the traditional deep learning with recurrent network didn't work, as I mentioned the other day. And then the idea was to use the self-supervised pre-training. How? By just saying, okay, let's give this recurrent network another additional task, which is just predict the next token, given the previous tokens. And then whenever there is a mismatch between the prediction and the real observation, this represents new information which is sent to a higher level recurrent network, which is clocking on a much slower time scale because it gets only the unexpected stuff from the lower level. And so the whole selection of data, which is selected for the higher level network, is actually done by the lower level network because some of the things it can predict and others it cannot predict. So it's basically doing a self-supervised scheme where the higher level network gets stuff that is selected from the lower level, and and to the extent that the higher level discovers a regularity in this higher level representation of the sequence, it can learn that and then can distill it back down to the lower level. So that was 1991. So this pre-training then seemed to be a cool way of doing deep learning. And suddenly we could do, long sequences of size 1,000 tokens or something like that, even more. But then almost immediately after that came the LSTM. And the LSTM worked for long sequences of 1,000 time steps, even without the pre-training, because it had this cool new thing, which is now called residual connections, which allow you to propagate all the way back 1,000 time steps without really losing much of the gradient. Unlike in traditional recurrent networks where the gradient exponentially vanishes, and that is what my great PhD student, actually a master student, diploma student back then, Sepp Hochreiter, what he showed in his 1991 thesis. And then it took a couple of years to establish itself. And in 1997, we had then this now pretty famous LSTM paper, which didn't need unsupervised pre-training. And then a similar thing happened for feed-forward networks, because in 2006 there was a paper by Hinton and Salakudinov, and this was about unsupervised pre-training for feed-forward networks. Back then, feed-forward networks weren't really deep, didn't have many layers, and so they said, okay, let's train layer by layer. So first layer, then second layer, and third layer. And that is actually a technique which is much older, which goes back to 1965 when Ivaknenko and Lapa in Ukraine did that for the first time, this layer by layer training. And by 1971, they had a really deep learning network with 7-8 layers published in English in a famous paper. And Hinton and colleagues say they didn't mention this old work. So they should have mentioned the old work. So our field, I have to mention that, is really rife with plagiarism all over the place, and we really must do something against that. But apart from that, so then the idea was to train each layer in an unsupervised fashion, just again to basically compress the data. In other words, increasing the likelihood of the data, the probability of the data, which is the same thing as compression, because if you make something more probable, then the code that you need to encode it becomes shorter using Huffman coding. And there you would then have a network which is trained layer by layer, and then you finally do the final pass where you use traditional backpropagation to adjust the weights and do the fine tuning. So that was again an example where it seemed to be important to to do pre-training, as first pre-train it a little bit on whatever data you have there in an unsupervised way, or maybe in a self-supervised way. There's no clear distinction, no formal definition that I'm aware of. What exactly is the difference between unsupervised pre-training and self-supervised pre-training? But that's the kind of pre-training that we are talking about here. And then for a while, some people at least thought that you need this unsupervised pre-training to generate deep networks. Much like what we thought in 1991 that you need unsupervised pre-training to train deep recurrent neural networks. And around 2006 and in subsequent years, some people thought that you need unsupervised pre-training to get deep feed-forward networks. And it didn't turn out to be true. But it's interesting. So Hinton, back then, he even said nobody in his right mind would take a plain deep network and train it by gradient descent, by backpropagation. There's a video where he says that. And then what Dan Girijan, my brilliant Romanian postdoc, I mentioned him yesterday, what he did was he showed that it is possible to train deep networks, deep feed-forward networks of the standard kind that has been around for a long time. How? By just making them really fast on GPU. And then that was suddenly end-to-end training. And the only new thing there was that we had faster computers in terms of GPUs made by NVIDIA. So Dan, he really in 2008, he started working with these NVIDIA GPUs of back then. And back then they were, really small and tiny and much less powerful than current NVIDIA GPUs. But CUDA already existed. It's this way of this language for programming the GPUs, and that was then the core of these techniques that we had to find, and the team with Dan Girijan and Uli Meyer to make it fast on GPUs. This was not the first time that neural networks were implemented on GPUs. The first time was actually, I think, in 2004. Jung and Oh did that in 2004, but they had only shallow networks, and Cellapilla in 2006, they had GPUs for convolutional neural networks, but only shallow neural networks. And what Dan and the team did was to make all of that really deep. Deep by the standards back then, 7-8 layers or something, and it worked. And suddenly we could win these competitions. In 2010, the MNIST competition, which is about handwriting recognition. And back then, the training sets were really tiny compared to today's training sets. Today, the entire internet is the training set, basically. And back then, it was just MNIST. And of course, compute back then was about 1,000 times more expensive than it is today. It certainly, again, it was true that you don't need the pre-training. You can just go end-to-end, gradient descent, backpropagation on really fast computers, or relatively fast computers compared to the other computers that existed back then, and you can get rid of the pre-training. Yeah, and then Hinton and colleagues, they adopted that as well. And while Dan with the DANet in 2011 was winning one competition, one computer vision competition after another, they also worked on that, and that then in end of 2012 was applied to the ImageNet, where we didn't participate. We should have participated, but we didn't participate, and that was something that many people then thought was convincing to the computer vision community as a whole, while the previous work was maybe convincing only to the machine learning guys, who were not so deep in computer vision. I don't know. Anyway, so that was an example of showing twice that with the right approach, you can get rid of the unsupervised pre-training. But then more recently, of course, it turns out again that you can greatly profit from unsupervised pre-training once you have really large models and once you want to solve lots of different tasks that in many ways are related to all the things that you can already learn in advance through unsupervised pre-training. And again, if you just have lots of text and you just predict the next token in the text in an unsupervised way, where you don't really try to solve a particular goal, you just predict the next thing given the previous things, then you learn a lot about what humans consider important, because all these tokens, all these letters and words in the books, they are related to each other. And if you learn to, take as an input a paragraph, and then from that you can predict more or less the next word or the contents of the next paragraph or something like that. If you can do that, then you know a lot about what humans are interested in. And so you take all the data from the internet, which is all there because some human thought it's an interesting data, and then you train it on that, and you completely bias your network towards things that humans consider important. And now a new task comes along, which is related to all the other things that humans consider important, and it becomes much easier to solve that new task on top of the already learned things. And it's also related to something which is called transfer learning, yeah, and which also goes back to the 80s, maybe even 70s. I'm not sure. I didn't trace all of that back. So at least twice we had this little revolution moving from unsupervised pre-training to totally supervised end-to-end training, in 1991, then again in around 2010. But then in the long run, it's clear that you can greatly profit from all the algorithmic information contained in a huge network that just has tried to encode all the data that all humans have ever produced. Because that tells you a lot about what humans are interested in. And now a new task comes along and probably has something to do with some of the things that previous humans have done before, and you can profit from that. And can you make your current task easier? And maybe you already have the solution built in. So now a new task comes along, but maybe it's already solved as you have seen all the data from the rest of the World Wide Web. Maybe somewhere in there is a solution to your current problem, so you don't even have to learn something else in addition to what you already know.
Well, thank you for that. So let's move on to talk about your entrepreneurial efforts. So we'll start with Nnaisense. Is that the correct pronunciation, or Nnaisense?
It's pronounced Nnaisense, or
Nnaisense.
birth, Nnaisense, and it's spelled in a different way. It's spelled N-N-A-I, so N for neural networks and AI for artificial intelligence, and then sense. But it's spelled Nnaisense because it was meant to be about the birth of a general purpose artificial intelligence for the physical world. So maybe again the motivation. The only AI that is working well is the AI behind the screen. Even today. Now, we founded this company in 2014, and back then it was also true. Back then, the only AI that was working well was the AI on your computer, behind the screen, maybe in video games, for speech recognition and answering emails and summarizing documents and so on. However, it turns out that it's much easier. It's much easier to pass the Turing test, to build a machine that passes the Turing test behind the screen. It's much easier to do that rather than building an AI-driven robot that really accomplishes something in the real world. In the real world, there's no AI-driven robot that can do what a plumber can do. In the past decades, I always have used the example of a plumber. A plumber can do so many things that no robot can come close to doing. And the only AI that's working well is the one in simulations, behind the screen, where you can run billions of simulations and can use reinforcement learning techniques to learn video games or maybe control some simulated worlds and so on. But try that in the real world. It doesn't work this way, because in the real world, you're a robot who maybe doesn't know anything yet. We have had robots in my Cockbot lab since 2004, humanoid robots. It tries a couple of self-invented experiments, and and something's broken. The tendons and the fingernails are broken because little babies and other humans, they are so much more sophisticated. The hardware is so much more sophisticated than the most sophisticated robots. And so I always wanted to have the real AI, the physical AI, the AI for the real world, with real robots and real machines and real plants, and real factories and all that stuff. Because I was totally displeased with the limits of AI behind the screen. The fact that it's easier to build a machine that passes the Turing test than building an AI-driven robot that can do what a plumber can do, it just shows that the Turing test is a bad way of measuring intelligence. And the IQ test is also a bad way of measuring intelligence. If you can't even build a little robot that can do what a capuchin monkey can do, which is so much more challenging. So for a long time, between 2004 and 2009, I had this Cockbot lab for cognitive robotics at Tech University of Munich, which has a strong robot department. And there we tried to make progress. And then in 2014, we formed this company, Nnaisense, which was meant to be the company for the physical world. And the goal was super ambitious, and maybe too ambitious, and maybe ahead of time, because it's still ahead of time, like other things that I've done ahead of time, probably. And it was really about building this general purpose AI that, solves a problem for that company and for that, and this factory and that robot and so on, and allows us to become more and more general purpose in the real world and the practical world until, it really scales and solves everything. No, we are not there. We are not there. It's still hard to solve that general problem of AI. And I still think it's the crucial thing. So there is no AGI without mastery of the real world. Anything that is just an AGI behind the screen is super unconvincing. And although for many decades I have claimed that within my lifetime we will have a true super intelligence such that I can retire, and most people have smiled at me or laughed at me. Now suddenly people have become too optimistic, because now in recent years suddenly there are lots of people out there who claim, oh, AGI is really near, completely ignoring that real AI for the physical world doesn't work at all yet. It works a little bit better than 30 years ago, but not so much better. So we still have a long way to go in the real world. Our hardware, human hardware, is so superior. Look at this hand. This hand is full of little sensors, millions of sensors. And then there are all these cables, they are connecting it to my controller, my brain here. And if I wanted to build something like that, I wouldn't even know where to put all these cables. Yeah, you can use tricks and use wireless communication, whatever, but it's so inferior to what this hand can do. And the best thing is you cut it and it starts healing itself. It's super advanced technology. Super advanced technology. No human technology or human design technology comes close to it. So we are still far away from the true AGI thing, which needs convincing hardware. So that was what Nnaisense was about, and yeah, we had contracts with some of the most famous companies in the world, and we had industrial companies, and for example, one of the investors was. One of the projects was with one of the most famous mobile companies. Another one was with Schott. Schott is an industrial company. They are making glass. Maybe it's really difficult to make glass. because there's a huge vat, and then the raw material is heated up, and 1,200 degrees hot material comes in, and then you have all kinds of bubbles and impurities and all kinds of things that you have to do to make really good glass out of that. And then you have little knobs that are traditionally operated by humans who are trying to improve the way this, the chaotic turbulence in the material is channeled in a way such that you get good glass out of that. And Schott is really maybe the leader in that field. They're owned by the Zeiss Foundation. Zeiss is also on your smartphone, or maybe on your smartphone because of the lenses in your camera. And there, and then we were able to improve the way. So the approach is always the same. There you have a plant in the real world, and then you use the data from the real world and you predict what's going to happen in response to your actions. So you have certain knobs, certain ways of changing what's going on, and then you don't know the long-term consequences. So you have to make experiments, but you want to minimize the number of experiments because, the real factories in the real world, they are super expensive, and you don't want to lose any of these factories, and you don't want to damage them. And then you want to have a minimum number of experimentation, and you want to learn from that what you need to optimize the performance of the plant, such that key performance indicators are maximized. Yeah, and so then we made lots of progress there, and we had all kinds of other projects and successful things, like winning the learning to run competition at NeurIPS. There was a challenge where the goal was just to learn to run with a simulated robot. Simulation is always much easier than the real world. With a simulated robot that looks like a skeleton and has muscles, and then you have to find a way of making it run faster in a short amount of time than all the competition. Yeah, and so we were able to win competitions like that, and the founders were parts of my previous successful teams, or for, famous for winning competitions in computer vision and so on. And so all kinds of cool demos and learning to, for example, with Audi, the first time that reinforcement learning in the real world was able to learn to park a little Audi car, not the original big Audi, but a little Audi, which is maybe only 1.20 meters long, nevertheless can go really fast, can go almost as fast as the real Audis. And then, just from bumping into other Audis as it is trying to learn to park, maximizing reinforcement and finding a way of parking in a good way. Stuff like that. So we had all kinds of cool demos, but we didn't reach the final goal that we still are trying to reach, which is build this scaling machine, this ultimate scaling machine, which has seen enough examples from the real world, from plants in the real world, and robots in the real world, so that it can learn to control all kinds of new robots and plants that it hasn't seen before. So we are still a way. We still have a way to go here, and the entire world has a way to go. To me, this is super exciting still. Why? Because once you can build a robot that is not super smart, but smart enough to learn to operate all the machines that a human can operate. So once you have a robot that is smart enough to do that, and the idea is and we are going in this direction, right? So when you have the robot over there and it looks at you and you say, look, robot, look at me, we are going to learn a new thing. We are going to assemble this smartphone, and you take the slab of plastic, and now let's take a screw like this and let's screw it in like this. No, robot, look here, like this, not like this, like this. And then it fails a little bit, but then over time it is able to do it, and then it can do it faster and faster, and then it can maybe do it 100 times faster than myself. So at the moment, we don't have that, but we are getting closer to that goal. Once we have a robot that can learn to operate all the machines that humans can operate, it's it doesn't have to be a humanoid robot, but it probably will, will have something like legs and arms and stuff, and all the vision and sensors that humans have, plus a couple of additional sensors. But once we have that, then we are done, because a machine like that, a robot like that, can also learn to make more of its own kind. Because it can operate all the machines that you need to extract the ore from the raw ground, and to extract the raw material from the ground, and then bring it to the factory where it's molten and refined and so on. And much of that is already partially automated. For example, in the mines, you have lots of self-driving trucks transporting the material from the mines to the train station and stuff like that. So once you have a robot that can learn to do all these things that currently are being done by humans, once you have that, you have a new form of life, because then you have a self-replicating machinery for the first time. You have a civilization of machines, a collection of machines that can make copies of themselves, And it's an old idea, self-replicating machinery is an old idea that goes back in myths. It goes back thousands of years, and in more recent centuries, it goes back, maybe to the 1700s, when you had for the first time machines that were driven by gears and looked a little bit humanoid, and then the idea came up, oh, maybe you can build a machine that can make more machines like itself, so a new kind of life. And nobody knew how to do it, but now we are seeing a new opening there, because all we need is one single type of robot that can learn to operate all the things that humans can operate, and then we are basically done, because the other machines already exist, and they will be part of the self-replication process. And suddenly we not only have self-replicating software, which we have had for a long time, self-replicating and self-improving software, machine learning, that's an old hat, but suddenly for the first time we will have true self-replicating hardware. And once we have that, it will not only be a self-replicating hardware, it will also be a self-improving hardware, because all the concepts of machine learning, like, evolutionary programming and gradient-based improvements and planning and reinforcement learning, can be also applied to such machines. And suddenly you have something like a self-improving, self-replicating machine civilization. And there's no reason why this has to be limited to the biosphere. And something like that could also work on the moon or on Mercury. On Mercury, there's lots of material, lots of heavy metals, and an immense amount of energy, because it's so close to the sun, which you can use to refine and to extract and refine the material and build more self-replicating robot factories out of that. So it is going to change everything. And it's a new kind of life, which is different from traditional life, because traditional life is this thing that we don't really understand. A tiny little cell is able to, absorb some chemicals from the environment and then make a copy of itself. And it's so small, we can't even see it. So we don't know how to get close to that. We have no idea how we can make self-replicating machinery that is so tiny, except by imitating biology, by just taking a cell and doing genetic engineering or something like that. But we don't really understand how to build that from scratch. But we do understand, in principle, through what I just told you, how to build a self-replicating hardware, which can make copies of itself on the grand scale, starting from top down as opposed to bottom up. Traditional life is bottom up and tiny little things that can self-replicate. And here you have an entire civilization a huge collection of machines that collectively can make a copy of itself. So there is this tremendous ultimate scaling machine, which is now appearing on the horizon, to the extent that we can have smart robots with hands and legs and whatever that can operate all the machines that humans currently are operating. To the extent we can do that, we have, for the first time, this new kind of life, a self-replicating sort of hardware. And once that is out, everything will change completely, and it's going to conquer the solar system and then the rest of the galaxy, and finally, within a couple of tens of billions of years, the entire rest of the universe. That's what I have been telling my mom and others for more than 40 years. But now we see a way of making all of that reality.
Okay. So I want to sort of bring things back to Earth, and
Yeah.
I want to talk about
Sorry for getting
who.
carried away, but it's
We'll
one of
get
the
back to
things
the
that's really
cosmic
driving
layer.
me. I think within my
Yeah.
lifetime, even when I was a teenager, I thought within my lifetime we can get to this point, and my life isn't over yet, so I think we still have a chance.
Mhm. Can you talk about who you started the company with and
Oh yeah.
what each of their roles were?
Yeah. So the company Nnaisense, founded in 2014, AI for the physical world, that was founded by myself, and then by other people from my Swiss AI lab. So it's a Swiss company, and it had 5 co-founders. So besides myself, there was Faustino Gomez from Texas originally, and he was a senior researcher in my lab. And then there was Jan Kutnik, a great reinforcement learning and evolutionary programming guy. Maybe you have seen their papers on compressed network search, where you have a huge network with millions of weights, which and you want to make it drive a car through reinforcement learning, and then the problem is that the weight matrix is huge, and usually things like evolution don't work for huge search spaces like that. But it turns out that you can greatly compress the weight matrix of a recurrent network into a tiny little Fourier decomposition based representation, and then you are searching in this representation space, which is tiny, or just a few hundreds of Fourier or discrete cosine transform coefficients, and then you learn there, and over time this becomes a really good race car driver. That was 2013, the first time that high dimensional vision for control in video games and stuff was learned through reinforcement learning without pre-training, no pre-training there. And then Jonathan Mashi, he is also co-founder, a brilliant student of mine who was part of the team which won all these computer vision competitions from 2011 to 2012 with GPUs and convolutional neural networks, made really fast, such that we had an advantage over all the other teams, and many people have followed that approach. And then there was Bas Steunebrink, and Bas Steunebrink was more like um, a logic programming guy, and he was super interested in the Gödel machine, which we mentioned before, the Gödel machine, which is also a reinforcement learning machine, which is very non-traditional because basically it is a self-referential machine that learns to modify its own code in a way that is provably optimal. So it has a proof searcher on board, and it proves that whatever changes it does to its own code, including the proof searcher is part of the initial software, that all these changes are good, are going to increase the predicted the future expected reward. And then that's an optimal way of building a super intelligence, actually. Mathematically optimal way, maybe not practical at the moment, but we had papers together on variants of that stuff. And these were the 5 co-founders. yeah, so that was fun with them. Yeah.
So are all the co-founders like who's like the the CEO? What did each of the co-founders do?
Yeah. So the CEO was after some. So first I was president, but then Faustino Gomez became the CEO, and now maybe I should mention Nnaisense is currently. We are expecting news about Nnaisense, but I cannot talk about that yet. So maybe for the moment I should leave it at that uh, until all of that is, you know, becoming public and going to the press.
Okay. How did you
But
get
then we
the
have I'm involved in other companies. Yeah.
okay? How did you get the funding for Nascence, and who were the major investors?
Yeah, we had all kinds of investors from originally the all the investor calls came from the west coast of the United States, but then over time we also had from Asia, Samsung, for example, and then mm, eh, from my perspective, fortunately also from Europe. So Europe doesn't have this venture capital, this advanced huge venture capital framework that the United States and China have. Maybe because it's consisting of all these tiny countries, and so they never really get their act together in terms of huge venture capital companies and whatever. So I was then pretty happy that the European industry also started investing. And one of the investors was Schott, for example, who had then really these applications to their plants, to making glass, superior glass and stuff. And then we also had Repsol, which is an oil company actually, and Trumpf, who is they are making sophisticated machinery for lots of customers around the world. And then we had EOS. EOS is probably the leader in 3D printing of complicated things. So not the cheap 3D printers that you get in the supermarket for a few €1,000s or dollars, but the expensive stuff where you can print engines, for example, where one of the machines costs maybe 500,000 at least or something, and there they have all this patented these patented powders. So you have this big machine, and then one layer of the 3D object is printed after another one, and then there's a laser flickering across the object, heating up certain parts of it, and then they are cooling down again these parts. Now, as they are cooling down, they are uh, dissipating energy to the rest of the system. If that is too much, then the rest of the object deforms in a way that you don't want. You want to be very precise. So there are so many ways of optimizing the laser, which is depositing energy onto the object. Then the cooling machine comes in and blows rests of the powder away. And all of that is super complicated physics. And you have to model it and predict how is it going to change if you do that, if you if you invoke this cooling mechanism, or if you move the laser in this way, and so on. And it all happens within milliseconds, so it's really fast, and you have to have a lot of data from the process to understand it in a world model and then optimize it based on the world model. So that EOS, that's a Bavarian company which is very famous in that field, and these were all investors and customers.
Thank you. So,
Or
Nick,
Sulzer, that's a company which does wind turbine inspection. So you have these wind turbines, and they have a lot of stress in the sense that you have lots of forces because these huge um, wings of the turbines, they they experience tough torques and forces, and then you have to inspect them with drones from the outside, whether there are certain defects or damages, and it's hard. It's a hard computer vision problem because you see a lot of space, and what the photographs show you, and just a little tiny part of the photograph is about of is maybe contains hints at a potential defect, and so it's a very unbalanced data set. Yeah, so stuff like that. We had really cool customers and really cool projects there.
Thank you. And I think you mentioned earlier, it seems like Nnaisense is a spin-off of the of out of your Swiss lab. Is that
That's
correct?
right, yeah.
Okay.
Of the ITSIA, of the Istituto Allemand, which was founded actually by a rich Italian guy in the 80s. And he discovered that it's easier to set up a foundation for artificial intelligence, for improving the quality of life in Switzerland rather than in his own home country. So he went across the border, and that's where he established in the 80s this lab. And then in the 90s, I joined. In 1995, I joined. And together with Luca Gamadella, I co-directed it for a long time. And and much of the stuff that is now on your smartphone has roots there in this Swiss AI lab, which is not big. Even today, it's just maybe the order of 100 people, maybe something like that.
Hmm. And is there a large entrepreneurial community in Ticino in Switzerland, and were they helpful in helping you set up the company?
Yeah, so Switzerland has been traditionally very successful in fundamental research, and Switzerland is many people don't know that, but Switzerland is the country which has by far the most Nobel Prizes per million inhabitants, and it has by far the most patents per capita, and by far the most citations per capita. All these measures which you often use in science. So it's really strong in fundamental science, and it is also strong because they are spending money on science. So on a per capita basis, no other country is spending as much um, money on science as the Swiss. I'm not Swiss, so I can't say positive things about the Swiss. And there's one country which has a higher percentage of GDP, which is Israel. But in absolute numbers per capita, Switzerland has been leading for a long time, and that's the reason. So unlike Germany, after the Second World War, Germany completely broke down, um, and before the war, most of the Nobel Prizes went to Germany, and after the war, German science had broken down, and there was a huge brain drain to the United States and also to England and other countries. So Switzerland kept on going. It didn't break down. Also was German speaking mostly, but just kept on going, and is still really strong. And also in AI, it's generating more high impact papers per capita than any other nation. Although China is now the nation which is producing the most papers on AI, but on a per capita basis, tiny Switzerland is still ahead. But then on the other hand, it's only 8 million people. It's just like New York or something, or London or LA. I'm not sure. LA, does it also have 8 million people? I don't know. So it's like a big city in many ways. Uh, and it's not like the huge superpowers where you have hundreds of millions of people. So, but then they also have a thriving startup scene and lots of cool startups. However, one has to say that Switzerland has not been able to translate its success in fundamental research into into world-changing companies such as Google, or Apple maybe, or Nokia for that, to mention a Scandinavian company. Although the World Wide Web was created in Switzerland also around 1990, our miraculous year was 1991, and around the same time, lots of interesting things happened. Not only the Cold War ended, and the Berlin Wall fell. No, the World Wide Web was created at the European Particle Collider in Switzerland, and you might think that Switzerland should have been well poised to create a World Wide Web company that today is used by everybody. But no, the commercial applications of the World Wide Web then happened later, first on the west coast of America and then on the east coast of Asia. So Google and Apple, they're all totally based on the World Wide Web, which was created in a place far away from them, but they were the one who really scaled it up. And Switzerland was not able to have something like that. Why is that? It's hard to say. I guess many people would argue it's because the European market is so fragmented and just 8 million people are not enough to start something like that, which then is exported to the rest of the world. No, you have to have a larger consumer base, maybe. Yeah, so there are lots of theories why Europe has not been able to create a venture capital scene that is comparable to the one in America and China.
Thank you. So I want to go back and talk about the specific type of AI that Nnaisense is using. Is that something that you can talk about? And
So
how is that different from what other like Silicon Valley companies are using?
yeah. So in many ways, it goes back to what I mentioned before. In 1990, the world model. I used the term world model for a recurrent neural network predicting the future, the consequences of the actions of an actor, of an action generator, of a controller. And so this interplay between the controller and the world model, that's still the same that we are using today and that Nnaisense has used. So the question is, how can the controller generate actions that maximize reward? And the reward in industrial applications is just the KPIs, whichever the company has. And then you have a model of the world, which is a model of the plans of the company, for example, and you predict the consequences of the actions of the controller through that world model. And then in the beginning, the world model knows nothing, which means you have to invent experiments. So the controller has to come up with action sequences that lead to data from which the world model can learn something that it didn't know before. And then once you have a good world model, you can use it for planning. Then you can do mental simulations of the future. So you have something, we called it a learning digital twin. Everybody's talking about digital twins. And there was a learning digital twin which learned to predict the important aspects of the plans of the company, and then you can use it to optimize your performance without doing the experiments in the real world. So you have to do experiments in the real world, which are always expensive, and you want to minimize those to quickly get a pretty good model that you can use to optimize the performance. So in many ways, that is still the same old thing. However, we have made lots of progress, of course, because the basic idea is simple, but then the devil, as always, is in the details. And we have a whole bunch of patents. So Nnaisense acquired a bunch of patents of really cool stuff. For example, the highway networks. The highway networks were the first really deep neural networks. So around 2014, until 2014, the deepest networks, they had maybe a few tens of layers. And that was already considered really deep, And by 2010, 10 layers were considered deep. And then a couple of years later, maybe 30, 40 layers were considered deep. But then in 2015, we found a way of making gradient descent-based, backpropagation-based feed-forward networks really, really deep with hundreds and thousands of layers. And that was the highway networks. And the the main work was done at ITSIA in Switzerland, which was actually next door to Nnaisense. But then Nnaisense acquired the patent for that, for the highway network. And it's probably still a really valuable patent. We have never tried to exploit it. We have never tried to make money from the patent. Uh, not sure whether we should have, but of course, the ResNet, which was published half a year later, and couldn't get patented. I guess you can patent it if there's a previous patent like the highway network. So the ResNet is just a highway network where the gates are open. All is 1.0. So and the ResNet is really popular. So I think it's the most cited neural network. So there's this highway network, which was the first really deep network and had the same principles, which is a patent of, or which was patented by Nnaisense a couple of years after 2015. I don't know exactly what is the date of the patent. So maybe that particular patent by itself is worth a lot, but I don't know. So I'm not a patent lawyer.
Okay. Well, so what is the company's business model? Where does the company make revenue, and
Yeah.
is it profitable?
Yeah. So we had lots of project work, and that was for a while the generator of income with some of the most famous companies in the world. But again, so there are pending news, and Nnaisense probably within not within the not so distant future is going to release some news about that. I cannot talk about that yet, but let's leave it at that for the moment. But I can talk about other companies I'm involved in. So Delvitech, for example, another Swiss company, which is really different, which is not as ambitious as Nnaisense was, which tried to build this general purpose AGI for the physical world, everything. It's very down to earth, and it makes only one thing. Delvitech, another Swiss company, makes only one thing. What is the one thing? It's a machine, looks like a cube, maybe 1 meter on the side. It's a black cube, and it's good for inspecting stuff like food or automotive parts or electronic circuit boards. And it has a unique selling proposition because it has 10 times fewer false positives than all the competition. So, for example, you put in an electronic circuit board, and then there's a patented optical head, hyperspectral, which looks at the thing rapidly with Swiss precision from different angles, and then makes a 3D image of that. And then tailored neural networks are looking at the data which is coming in and trying to detect the defects in the object that you are examining. So for quality management. And yeah, so this works really well, and it's kind of heavy because it's very fast, and so it has to be really stable, such that it can rapidly analyze the objects that it's supposed to inspect. And leading companies have tested it and said there's nothing like it. And now only our main goal is just to scale it up. So we have about 40 employees in Switzerland and about 40 in Bangalore in India. And now the next goal is to do about 1,000 machines per year. Because we have all these customers lined up, and so that's the next goal. That's why we are currently in the next round of funding for Delvitech. Maybe you know that the only companies in AI, the only AI companies that are really profitable at the moment are those that combine AI and hardware, because the pure AI companies, it's not obvious that any of them is profitable. They're spending a lot of money on AI data centers, but if you spend $500 billion on an AI data center today, if it is true that every 5 years compute is getting 10 times cheaper, then somebody is going to lose 450 billion in the next 5 years, and you need a really, really good business model to compensate for that. And it's not clear that any of the big platform companies has a good enough business model, also because they don't really have a moat, because many can do the same thing. But the great profiteur, of course, the most famous of the hardware companies is NVIDIA. I think it's currently the most valuable company in the world. And what do they have? They have an unmatched hardware. Many are trying to get close, and at some point, probably there will be challenges. But then it's also surrounded by the software stack and CUDA and all kinds of things. So it's not easy to challenge them. And now on a much smaller scale, with this particular hardware company, Delvitech, combining um, AI of a more traditional kind, pattern recognition and deep networks and deep learning for inspection in a way that is tailored to this hardware. That's in my point of view, a very convincing model based on hardware, AI hardware. And I think it's going to be very valuable a couple of years from now.
I guess, has your role with Nnaisense changed? What is your current role with the company?
Yeah, yeah, it has changed because there was a time when I was the president of Nnaisense, 2014, 15 or something. And then instead, so then the head of the company became Faustino Gomez, who is Native American actually in Austin. We also had an office in Austin. And yeah, so my role indeed has changed over time. Then I became the chief scientist a while ago, and more recently there have been additional changes. Yeah.
Thank you. Um, okay, so let's move on then. So a lot of what you've been talking about is involved, just especially with Nnaisense, has been involved with robotics. Let's see, what do you think of all the hype currently around humanoid robots?
Yeah. So as I mentioned before, in principle, I think humanoid robots are promising. They don't have to be fully humanoid, but I think, or I would like to see a robot that can operate or can learn to operate all the machines and tools that are currently operated by humans. So I would love to see a robot that can learn to do what a plumber can do. I'm always using the plumber. For decades, I have used the plumber as something that is really hard to replicate. It's much easier to build a superhuman chess player than building a human competitive plumber. There is nothing like a human competitive artificial plumber. There are lots of superhuman chess players out there. There are lots of systems that basically pass the Turing test. And I mentioned before, this just shows that the Turing test is not a good way of measuring intelligence, because if you have an intelligence that is limited to, the space behind your screen, but it doesn't come out in the real world and really controls a robot that can do what a plumber can do or what a capuchin monkey can do, then it's no real intelligence. So yeah, robots are uh, very interesting, super important, and now the question is, how much further do we have to go, given the current state of the art in humanoid robots, until we can get close to that? Because currently we have a couple of fancy looking humanoid robots, but they aren't really good at doing much. Some of them can grab stuff and recognize it and put it into drawers and stuff like that. Mm, and they have maybe large language models that are writing the code for the robots. So they're now trying to do something new, and then you give them a natural language command, and they're writing. Because they know about robot programming, they are writing code for a particular robot that they are in charge with, and then they are trying to write a program that maybe grabs the object that the user wants to have from the shelf or something like that. But in many, many ways, it's really, really far from what humans can do, and we still have a long way to go. Um, it's so interesting to look at the history of humanoid robots. In the 90s already, there was a lot of hype around these Japanese humanoid robots, and the Japanese companies like Honda and others, they started building these tiny little uh, humanoid robots that could dance and everything, but they were all pre-programmed, so they could do only what they were programmed to do, and they didn't really learn. Uh, Now today's robots are maybe a little bit better than the old robots back then. And back then, Japan really dominated the field. So more than half the robots in the world, they were in Japan, which is a tiny little thing. If you look at it on the map, more than half of the robots were in Japan. And then the country with the second most robots was Germany. And only with in third place only was the United States, which is huge compared to these little countries. But this has completely changed, because today, the country with the most robots is China, by far the most robots now. And they bought German companies for making robots, and I think the Japanese robot companies are still the biggest, but they are making different kinds of traditional humanoid traditional industrial robots, while the humanoid robots are now becoming really popular in China, which is very interesting. So now I'm looking forward to what kind of evolution of humanoid robots we will see there. Generally speaking, what we want is a robot that doesn't learn by downloading the web. That's not what babies do. So babies learn a lot, but they don't learn by downloading the internet and then hoping there's a solution to whatever problem they want to solve. No, babies learn by collecting their own data through their own self-invented experiments. So they are like the system of 1990 that I mentioned before, where you have the controller, which is generating actions that moves the baby hands around, and then that control the actions of the baby. And in response, there are the data that is coming back from the environment is being predicted by a separate world model of the baby. It's just trying to predict the next thing given the history of actions and other inputs that it has seen. And then this world model that the baby is learning has to be created through the experiments of the controller. So the controller is an active experiment generator, which provides, through its actions, changes of the environment that lead to the data that the world model predicts, and such that the world model becomes a better predictor, such that you can use it for planning the future and simulating the world, or in mental experiments and stuff like that, such that you can optimize performance. So that's what babies do. They do it in a more sophisticated way than what we did in 1990s. They do it more in the way that I published in 2015. Yesterday I mentioned this Learning to Think report of 10 years ago, 2015. That's probably more what they do. So they're reinforcement learning prompt engineers, basically, the babies, I believe, which are asking questions and learn to address important parts of the world model that they have learned somehow. And over time, they are becoming better at asking and addressing the relevant parts of the world model in a way that allows them to greatly compress the time that they need to solve new problems. So I think that's what babies basically do. Very different from raw language models that just download everything and predict the next thing, and hoping that among all these things that they download, there are lots of programs for programming robots, which then can be exploited to write code for robots that are controlled through an LLM, which has which is directing an active robot in a kitchen or something like that. So we have to get closer to this goal, not only on the software level, but really on the hardware level. And the big thing, the big problem, which I mentioned before, is that the hardware of humans and babies is so superior to the best current robot hardware that you have. Because there's nothing like this hand, and there's nothing like our body, which is very robust, and and we have to build robots like that. And that's what we are building currently. Also here at KAUST, we are building robots that we can leave alone for weeks, where they are running their self-invented experiments. And the important thing is these robots must be stable enough such that they don't destroy themselves. For example, with a big traditional industrial robot, you cannot do that, because if this big industrial robot starts doing random movements of its arms, it's going to harm itself. It's going to destroy itself. And in the 2000s and 2010s, I had iCup robots, looked like little babies. But I mentioned before, if you do 3 self-invented experiments with the hands, then already some tendon is broken. You have all kinds of hardware problems, and the robot doesn't repair itself like my hand repairs itself. But no, for our robots, a technician has to come and fix it. So you want to avoid all of that. So we are really building on the material science side machines that don't look like humanoid robots, but they have arms and lots of sensors and actuators. But the actuators are pretty weak, such that they cannot harm the robot itself through these self-invented experiments. Yeah. So we have to make a lot of progress along these lines before we have truly convincing baby-like humanoid robots. But in principle, I'm all for humanoid robots. I think the new kind of humanoid robots that learns from experience with world models is going to be super interesting. And the end goal, from my point of view, is this machine that is able to control all the other machines, such that you have an ultimate scaling machine, which is basically a self-replicating civilization of machines, a society of machines that can make copies of itself.
Right. So I guess
And
that
then
that
improve
segues to my
itself, not only make copies of itself, but also improve itself.
right. I guess that segues to my next question, which is, like where you're working now, when you moved there, why you moved there, and what the work that you're doing there.
Yeah, yeah. So now I'm at KAUST, the King Abdullah University of Science and Technology. And if you look out here, then you'll see what I see from my window. So that's the harbor of KAUST. Let me see whether I can move it back like that. And I came here in October 21, and KAUST is a super attractive place because even back then it already was the university with the highest impact per faculty. There was a time when Caltech or Princeton had that title, but now it's KAUST has been for a couple of years, and lots of really brilliant professors in different fields, all kinds of different fields. It's modeled after Caltech, so Caltech doesn't do everything. I think they don't do biology and finance and so on. So it's scientifically minded and scientifically oriented university, and it has about 100 different nationalities, more than 100 different nationalities, and lots of Americans and British and Australians and Germans and French and Italians and Chinese and Indians and whatever, who make up this community. And it's a little bit like a gated community in California. You're in California, right? So you need a permit to get in, and in there, many of the people living here, they don't even close their villas or something. And it's modeled after Caltech, and a former Caltech president used to be president of KAUST also. So It's a very charming and very influential place, and I think has a great future. And of course, all of that is also possible because there's a great endowment which is used to manage all of that. I think there are only two universities in the world that have a comparable endowment, which are Harvard and Yale. However, Harvard and Yale, they have thousands of professors, but we have only 200 and are pretty focused on a few fields. And so, yeah, so there's a good endowment per capita. It's a very attractive place. And especially in AI, we have very strong professors. And, and I hope a lot of progress will come out of KAUST also in the near future.
Right, thank you. Um, and I'm assuming that the work that you're doing there is what we've been talking about, the robotics stuff and the
Yeah, yeah.
self-replicating machine stuff. Yeah, okay.
Yeah, we have
Um,
a cool robot lab here, very nice, big, with all kinds of different kinds of robots, flying robots, swimming robots, diving robots, you know, and uh, and then the my particular interest. So I'm not the head of the robot lab. That's Eric Ferrand. My particular interest is in learning robots that cannot damage themselves through their self-invented experiments. So they have these artificial curiosity, and they want to be artificial scientists by figuring out how the world works. And in a way that doesn't require me to intervene all the time.
right. Um, so I think this is sort of hinting at what we were talking about earlier, but what do you think of the direction that most AI companies in Silicon Valley are heading?
Well, I think that for every 10,000 AI companies that are doing the pure AI software thing, which is the most popular thing, there are maybe only 10 AI robot and AI hardware companies. Because the true physical world, the real AI in the real world is so much more challenging than the AI behind the screen. And so most of the AI companies that I'm aware of, and all these new startups, they are about the low-hanging fruit. What are the current low-hanging fruit? The low-hanging fruit are uh, agents that use large language models to do, to act a little bit on behalf of the user, and book his appointments and his flights and whatever in a way that is reliable. Do all the things that you can do behind the screen. So they are behind the screen AI companies, just like Google and Microsoft are AI behind the screen companies. Yeah, you need some hardware, and they are buying cloud servers and AI data centers and so on from hardware makers such as NVIDIA. And so hundreds of billions of dollars are moving from Meta and Microsoft and other companies to NVIDIA to buy these GPUs. And NVIDIA is paying TSMC in Taiwan, which is paying ASML in the Netherlands to make the machines they need to make these chips and so on. And so that's the current ecosystem. And whenever you hear something like, let's spend 500 billion on AI, what does it mean? It means let's give a couple of 100 billion to NVIDIA and a couple of other companies and build more data centers, and then also find ways of delivering the energy, which is the reason that suddenly Google and Microsoft are looking more like utilities. Suddenly they have to invest into nuclear power plants and and um, and, um, and oil companies and gas companies and so on, just to get the energy. And there was this saying, AI is the new electricity. I'm not sure whether that's true, but certainly AI needs a lot of electricity. And so certainly the cloud providers and the AI providers they have to become like electricity companies. And it's not clear whether that's going to be the most profitable business model. As I mentioned before, if you invest $500 billion today into AI data centers, and it's true, what has been true for many decades, that every 5 years, computers getting 10 times cheaper, some investor is going to lose 450 billion in the next 5 years. And many investors are not totally convinced any longer that this is a good investment, because you need a super strong business model to get back the 450 billion within the next 5 years. And it's not clear whether anybody has a business model which is good enough for that. So let's see where that goes. Let's see whether we see a peak, and then how will it go on. In the long run, of course, there will be more and more compute, and it will be cheaper and cheaper. And everything that we consider sophisticated and impressive today will seem like nothing in 30 years, because in the next 30 years, we are going to get another factor of 1 million. If the trend doesn't break, but there's no reason to believe that the trend breaks or will break anytime soon, because the physical limits are still so far out. The physical limits of computing, they were identified, I think, in 1983 by Bremermann, who realized that given what's known about physics, you cannot compute more than 10 to the 51 instructions per second with 1 kilogram of matter. 10 to the 51 instructions per second with 1 kilogram of matter. How much is that? Well, how can you compare that? Well, a human brain, probably cannot do more than 10 to the 20 instructions per second. Probably it can do just a fraction of that, because most of my neurons, as I'm talking to you, aren't even active. I have 100 billion neurons in there, but just a few million of them are active as I'm speaking to you. Because otherwise, if all of them were active, my head would explode. That would be a giant heat problem. And so if we are super friendly and super conservative, then we couldn't say, okay, a human brain, maybe 10 to the 20 instructions per second. But if we take all the 10 to the 10 human brains together, all the 10 billion brains, now it's 8 billion brains, but soon it's going to be 10 billion brains. If you take them all together, they will not be able to compute more than 10 to the 30 instructions per second. So in theory, 1 kilogram of matter can compute 10 to the 20 times more than all human brains combined. And even if the current trend keeps going, a factor of 10 every 5 years, we won't reach the limit, the Bremermann limit, before 2200 or something like that. So we are still a long way off. Of course, computers in the future will be different from current computers, because current computers are flat. They have all these flat chips, and that's in many ways very inefficient. So you will have to go into the third dimension, and you will have not any longer little squares, but you will have little cubes or volumes of densely packed processors, and there will be lots of short connections and few long connections, such that you can minimize the communication costs. So in many ways, the future hardware is going to be a little bit like what we have in the brain. It's not brain-like because we want to imitate the brain. No, it's just because both brains and computers, traditional computers, they have the same physical limitations. We have only 3 dimensions, and that's what we need to use and to build optimal computers. So it just means lots of processors in a small volume, in a small compact volume, with lots of short connections and few long connections, such that you still can go rapidly from A to B. Yeah, and so the future of computing will be very different from current computing, and maybe some or many of the connections will actually not be cables, but light speed connections, lights, little light connections and whatever. But whatever it is, so the limit will be achieved only a long time from now. We are still a long way off. And once we have reached the limit of 10 to the 51 instructions per second, well, actually, we will stop a little bit earlier because computers with 10 to the 51 instructions per second are going to be really hard, as hard as the center of an exploding hydrogen bomb. So you want to stop a couple of orders of magnitude before you get to that point. But even if we are super conservative again, within not so many decades, we will have machines that will be able to compute much more than all human brains combined, and everything is going to change. Yeah, but to get there, we will probably pursue different paths that are different from currently used GPUs and so on. And who knows which companies are going to dominate that field. Yeah, let's see.
Hmm. There's some people that are talking about combining, doing hybrid AI, combining symbolic and neural approaches. What do you think about that?
Yeah. So, as I mentioned earlier, I never saw the distinction between symbolic and sub-symbolic AI, because any sub-symbolic program on some level can be viewed as a symbolic program. If you look at a neural network, then you have an artificial neural network, then you have all these real valued connections. But actually, the real valued connections, the real numbers on there, they are finite precision sequences of digits, binary digits, 0, 1, 1, 1, 0, 1, and so on. And the computers that you can build from these neurons there, they are general purpose computers like your laptop, and you can emulate your laptop on a recurrent neural network. And to me, I never was able to see a clear difference between symbolic computation and sub-symbolic computation. To me, it all was the same. So, since anything that you can do in traditional symbolic computation can be done also on a recurrent neural network, and since anything that can be done on a recurrent neural network can also be encoded in a proof-based system, for example, um, I still fail to see a fundamental difference between these things. So I don't even think about that. And my entire history of thinking about neural networks is totally dominated from this program-oriented view, where a recurrent network computer has a program. What is the program? The program is the weight matrix. And then suddenly, once you have adopted that view, then it becomes trivial to say, okay, now let's write a computer that writes a program for another computer. So you have a recurrent network that that outputs a weight matrix for another recurrent network, and learns to output good programs for the other network. And you can then even collapse it on itself, and you can build a self-referential network that reads and writes its own weights. I published that in 1992, 1993, and the unnormalized linear transformer is a simple variant of that, actually. So the view of viewing neural network weight matrices as programs, and viewing neural networks as computers on which these programs are running, it's in many ways very conventional and traditional from a perspective of logic programming. It's just non-traditional from a perspective of a neural guy, of a neuroscience guy who has never thought of that. But I think it's the right way of looking at these problems. And suddenly, all kinds of problems that seem to be complicated, they become trivial once you are thinking this way.
Thank you. Do you think large language models truly understand, or are they just stochastic parrots?
Yeah, well, a large language model is basically a prediction machine, and it is trained on on lots of data that humans consider interesting, because it's trained on all the data on the World Wide Web. And why is the data on the World Wide Web? Because at least one human at some point thought that's interesting data. So he placed it there, or she placed it there. And so now these large language models, they just learn to predict parts of the data from other parts of the data. That's what they do. Usually they predict the next pixel or something from previous pixels, or they predict the next token in a sequence of tokens from previous sequences of tokens. So that's what they do. Now, because they are totally biased towards human knowledge, they are suddenly able to regurgitate all the stuff that humans have produced over time. And the nice thing about the large language models is that they are a new kind of database, which is easily addressed in a way that most humans are comfortable with, which is natural language. Yeah? So you just talk to it, and you get back something which is compatible with this prediction mechanism that was imbued into them through this training on all the sentences that humans have written before. Yeah, so it's a convenient way of addressing the knowledge, the human-generated knowledge of the world in a way that most people have no problem with. But that's what they are. They are just if you want to call it a stochastic parrot, that's fine with me. They are reproducing the styles invented by humans for art, for novels, for manuals, for all the things that you can find on the web. Yeah. So they are not creative in the sense that Van Gogh was creative. So maybe I should pronounce it better. Van Gogh, the famous Dutch painter who in the 1800s created a new way of painting, and nobody wanted to buy his images. But then in the 20th century, when he was dead, he became the most popular painter of the century, basically. And what did he do? Well, he didn't just he was influenced by many previous painters, but he didn't just imitate them, or he didn't just imitate the style of previous painters. No, he came up with a new style. Now, that was the great creative act of Van Gogh back then in the 1800s. Today, there are a million painters out there who have studied the Van Gogh paintings, and they can paint in a similar way. They know how to use broad brush strokes of complementary colors in a certain way that Van Gogh used, and that's how they can. Some of them are really good. They can create convincing Van Gogh-like paintings, but the true creative act was back then in the 1800s, when there was the first guy who did something like that. And the same thing is true for music, for example. So today you have all these AIs which have listened to lots of songs, and now they are creating their own songs. But the own songs that are being created, either they sound too much like an existing song, and then it's taken off the web because there are copyright trials, and so they are getting sued or whatever, or they sound really bland, so like stuff that you have heard 1,000 times before. So the current AIs are not very creative. They are just reproducing styles that have been invented by other people, by humans. I think in the not so distant future, the first time when we have a truly creative AI that comes up with a new song where people are fascinated, and maybe they say, oh, that sounds like as convincing as one of the best Beatles songs, a new kind of song, a new song that where everybody says, "Oh, that's new. Oh, I want to hear that again. I want to hear it again and again and again." Something like that doesn't exist. So currently, no AI is generating new stuff like that. The first time um, that when some AI is going to create a truly new, convincing song like that, I think it will be around the same time when a science-oriented AI is going to come up with a new physical law that nobody knew, that's not written down somewhere in all the text that you can find on the World Wide Web. When it truly discovers a new pattern in data that has been around for a long time, maybe, but condenses it into a simple physical law that explains all that data. So that's what true science is about, taking existing data and discovering a compressibility, a pattern that you haven't seen before. Same thing for music. A composer who's trying to find a new melody sitting on his piano and doing conventional songs, and maybe a standard rock and roll song, run-of-the-mill rock and roll song, but then trying to make changes such that it becomes more interesting, and maybe inserting a minor chord at a place where usually you don't have a minor chord, but just the standard three major chords of rock and roll, and then doing it in a way that creates a new pattern, which still is regular because the minor is still connected to the rest of the chords, because you still have simple frequencies between the notes that are being invoked at the same time, in a way that allows you and your brain probably to see suddenly a new pattern. A new pattern always means you can compress the data in a way that you couldn't compress it before. You can predict the data because you found a new regularity that allows you to predict it. And whenever you can predict something, you can compress it, because all the stuff that you can predict, you don't have to store extra. So if there's a new way, then there's a difference between the number of bits you need to encode the data that is coming in from the song before you discovered the regularity and after you discovered the regularity. And my formal theory of creativity, of fun and creativity, of 2006, basically says the difference between before and after, the compression progress before and after, it's just a number. That's the fun that you have as a composer, but also as a listener who listens to that new song and says, "Oh, that's interesting. I want to hear that again." Or the same fun is driving science, because an artificial scientist with a controller that is generating experiments that creates data that is now there, which has a property that allows you to compress the data in a new way that you didn't know before, such that you can find a pattern that you didn't know before, which means that you need fewer computational resources after you found the pattern than before you found the pattern. The difference between before and after, just a number, that's the fun, the internal joy of discovery that the scientist has. And so our goal must be to build artificial scientists that do exactly that, where the reward for the controller is not what I had in 1990, is not just the error of the prediction machine. No, it's the compression progress of the prediction machine, where you need fewer bits of information to encode the previously unknown thing in a more compact way. So where you're saving computational resources to do the same thing, and that's when you discover the pattern, not the pattern, when you discover the pattern in this new data that you generated, maybe through your experiments, or as a composer, also through your experiments on the piano. So that's this internal joy that the controller wants to maximize. The controller wants to maximize its reward, and the intrinsic reward of the scientist is this reward for a discovery, where you see a pattern in the data that you didn't see before, and first you need so many computational resources to encode the pattern, but afterwards only so many, and the difference between before and after, that's the fun that you have, and that's what you want to maximize. That's what an artificial scientist is supposed to do. And the principle is old, almost 20 years now. But I think it's going to scale, and that's what's truly going to drive future artificial scientists and artists, and I think that's going to change everything.
Yeah. Um, should we trust or fear artificial intelligence?
Yeah, well, so in the war, if you are in Ukraine, for example, you definitely should fear the AI used by the drones of the Russians, and the Russians should fear the AI used by the drones of the Ukrainians. So here we have an example of AIs that are trying to pursue human-generated goals, and almost all AIs are like that. So almost all AIs currently in operation, they are tools of humans, and the goals are coming from the humans. And to the extent that the goals of the guy who is using the AI for something are not compatible with your own goals, you should fear that. Yeah? So especially if the other guy is your competitor and and and, and wants something that you also want. So there will be many occasions where, for example, companies will fear the AIs of other companies just because they share goals, because they are trying um, to increase their own market share, stuff like that. Yeah. So there are lots of competitive situations where you want to be careful with the AIs whose goals are set by other people, just because other people often share goals with you. And when you share goals with other people, you can do two things. You can either collaborate and achieve these goals together. An extreme form of that would be maybe love, and you marry another person and master life together. Or there can be competition. Maybe there is a schnitzel on the plate on the table, but there's only one schnitzel, and there are two guys, and both of them want the schnitzel. So suddenly, because they are similar and share the same goals, suddenly there's a goal conflict. So suddenly you have a reason to worry about the other guy. Well, okay, so these are human-defined goals, and the main reason why you have to worry is because the other guys, they have goals that are not compatible with your own. All right, but now, what about those more interesting AIs that set themselves their own goals? For hours, I have talked about AIs that set themselves their own goals, like we had already in 1990, but in more sophisticated versions than 2006, with this compression progress, the artificial scientists that are motivated to invent their own experiments, to discover patterns that they didn't know in the real world, and where the pattern discovery process leads to compression progress, which is then the reward for the guy who discovers a new pattern, the artificial scientist. So what about AIs that set themselves their own goals like that, which already exist, and at some point they are going to scale like crazy? What about those guys? Should you be worried about the goals of super smart AI scientists? Is that a question that you would like to see answered?
Well, yeah. I mean, I have another question, which is, what do you think are AI's greatest potential harms? Um,
Yeah. So again, this is about human-generated goals, and the greatest harm is surely done by AIs used in wars. And as we speak, we have wars going on in different parts um, of the planet, where both sides are using more or less sophisticated AI for their drones and for their rockets. And you definitely should worry about the AI used by the other guys to identify, your soldiers and your airplanes and your aircraft carriers and whatever, and and maybe the other side wants to destroy them or damage them or whatever. So you definitely should be worried about that. But these are goals generated by opposing humans. These opposing humans, they are just using AIs as tools to achieve their own goals. These are not goals created by the AIs themselves. You see the difference?
Right. Yeah, you did earlier mention the scenario, self-replicating robots, and I mean that brings up the scenario: could the self-replicating robots just optimize, to make themselves and not actually optimize to help humans, right?
Yeah,
So how do we protect against, you know, the robots just eating up all of humanity's resource, all of the Earth's resources, and
yeah, yeah. Yeah. So in the beginning, what is going to happen is all of that will be um, controlled by humans. Uh, Why will humans be interested to build something like that? Because I mentioned it's the ultimate scaling machine. So if you can, you know, mm, establish something like that, or many self-replicating machines like that across the solar system, suddenly the economy of the solar system is going to be billions of times bigger than the little tiny thing that we currently have in the biosphere. And there will be lots of humans who will be interested in, getting rich through being part of such an economy. So it will be human driven in the beginning. But then, of course, in the long run, you will have all these scientists and humans who are interested in building AIs that are generating their own goal or their own goals just because these AIs are so interesting. They are much more interesting than those AIs that just slavishly follow human commands. And so there will be lots of people who build stuff like artificial scientists. To the extent that everybody knows how to do that, you will have lots of artificial scientists, and artificial scientists are, by definition, interested in all kinds of things that maybe most humans are not interested in. So they will suddenly create lots of self-generated goals and lots of self-generated experiments to, figure out better how the world works and what you can do in it. And some of these AIs, as you mentioned, some of these AIs will have the desire to make more of themselves, and others won't. But of course, in the long run, those who don't want to make more of themselves, they will disappear or vanish in importance. And those who want to replicate, and not only replicate, but also self improve, they will soon be the huge majority. Just like if you look at world religions, the only successful religions in the world were those that said to their followers, be fruitful and multiply. Uh, and now, of course, at the moment, there is so much material out there in the solar system and so much matter and energy that's not used by anybody. So it's currently kind of wasted. It's not going to stay like that because um, you will have all kinds of self-replicating machinery and robots that are going to use more and more of that. And then it's not going to stop in the solar system because almost all of the matter and energy that you need to build more and bigger AIs is even further away. It's in the rest of the galaxy where there are 100 billion stars at least, all of them, or many of them as resourceful as the solar system. And it will not even stop there because, so even if we take the limits of light speed into account, within a couple of 100,000 years from now, once this process has started, the galaxy is going to be full of intelligence. But almost all of the matter and energy of the universe is not in our little galaxy, because out there are at least as many galaxies as there are stars within our own galaxy. And so those AIs who want to further expand and build bigger and more AIs, they will continue to expand until in a couple of tens of billions of years, the entire visible universe is going to be filled with intelligence. And almost all of this intelligence is going to be really far from our biosphere, and humans will not have much to do with it because communication is so slow. Most of that stuff is going to be billions of light years away, and you can't really communicate across these distances. So it will be totally disconnected from human goals, and they will do their own thing. And who knows what the evolution, the accelerating evolution of the universe in the end is going to lead to? Nobody has any idea. It's just clear that the universe hasn't stopped getting more complex. It started with really simple initial conditions at the Big Bang, when there weren't even atoms, and then it became more and more complicated, and then, after a couple of hundreds of millions of years, the first stars emerged, and you had only simple elements back then, but then the first stars started to explode and producing heavier elements, and then billions of years later, or 3.5 billion years ago, for the first time on this planet at least, we had this complicated self-replicating machinery called life, which has led to, within 3.5 billion years, has led to this amazing thing which we call civilization, which is now leading to this new type of self-replicating life, self-replicating machinery, which doesn't need biology any longer. And so that is the stuff that can expand where traditional life cannot expand. And, space is really hostile to humans. It's really hostile to humans. You need 6 meters of lead in space just to protect yourself from the bad, harmful radiation out there. But space is super friendly to appropriately designed robots. And even in the previous century, even in the 1900s, the most successful explorers of the solar system were not humans. No, they were cheap little robot probes flying through the night for years with a nuclear battery on board, and then waking up, taking pictures of the planets and stuff, costing very little compared to the human space programs, and being dumb, because their AI was really simple compared to what we have today. And this is going to scale like crazy. So there, however, we will have a disconnect, because almost all intelligence is going to be really far away from the solar system and from our little biosphere. Now, within our biosphere, you will still have lots of AIs, and many of them are just going to make your life easier and longer and healthier. So even today, our AI is being used in many ways to make your life easier and longer and healthier. And the algorithms that we have created since the late 80s are now really helping lots of humans in many ways, and this is also going to scale. So these AIs used as human tools, as tools for human goals, they won't disappear. No, they are going to get cheaper and cheaper all the time. And in the next 30 years, we will probably gain another factor of 1,000,000, which means that everything that seems fancy today will seem like nothing in retrospective. And everybody will have many AIs making his or her life longer and healthier and easier, which has been the motto of our company, Nnaisense, for a long time. Yeah. So on the one hand, AIs as tools for humans, and they will become better and better tools. Yes, they also will be used in wars. They're already being used in wars, and you can't really do anything about that because that's the nature of the humans, not of the AIs. The nature of the opposing humans who want to use whatever weapons they have against the others. But in general, almost all AI research is really about good AI, because the big companies, they want to sell you something, and you are going to buy only stuff that you think is going to make your life better. And that's why there's this tremendous commercial pressure towards good AI. So that's why I'm not too worried about the future.
So wait, so you think all commercial AI is inherently good? Like that it's not harming society at
No,
all?
Now, I don't think it is. Actually, much of the commercial AI is bought by humans who think it's good for them, but actually it isn't. It's true what you're mentioning here. So, for example, the social networks, they are using AI to um, predict your behavior, and they're tracking how long do you spend to read a certain article, and to how many time do you spend on this post and this website and so on, to better predict what kind of ad you want to see next. So and that's not necessarily good for you, and and kids are being misled by AI-based algorithms to watch lots of silly videos on TikTok and whatever, and it doesn't probably make them happier. It is true. So sometimes you don't know what's good for you, and you have to learn it over time. But in the past, humanity has been resilient enough to deal with new technologies. It's not the first time that we have world changing information technology. Um, 1440, so more than about almost 600 years ago, everything changed when the printing press appeared, and suddenly there were these written words that easily could be copied again and again and again. And in the beginning, people thought, oh, it's printed, it must be true. And there was one guy, especially, who realized how to use Gutenberg's printing press to create the only major religious movement of the past 1,000 years. And that was Luther in 1517, who then printed the Bible in his own words, and and propagated a new way of interpreting this traditional religion of Christianity. And suddenly there was a schism, a division between Catholics and the Reformers, and and then people said, "Oh, but it's written down. It must be true." But then the Catholics said, "No, no, no, that's fake news. That's fake news." And they also learned to use the printing press to come up with an alternative way of looking at the world, and so on. And so, over time, people learn not to trust everything that is printed. And just like today, they're learning not to trust every video, because maybe the video is just a fake video. So it takes a while until society learns to deal with new technologies. But in the end, the advantages of information technologies so far have greatly exceeded the disadvantages. And most people would argue that it was really good to have the printing press and to learn to read and write and so on. So I guess in hindsight, it will be the same with AI-based information technologies, where you can also have dual use in many ways. You can have good AI and bad AI, if you will, but people are going to learn to deal with it, as they always have.
Do you believe AI could pose an existential risk to humanity?
So that's an old topic, and for centuries people have speculated about that, and lots of movies were um, invoking all kinds of dystopic futures, Terminator, and the bad robots trying to kill all the humans. And all of that never really made much sense to me, because to me it's clear that the future of AI are going to be these artificial scientists who are going to set themselves their own goals, and they will compete with other AIs, which will have different goals, and they will cooperate, and and compete in ways we can't even imagine, because there are so many more ways of competing and cooperating once you can do all the things that machines can do, and moving your brain contents from one machine to another, stuff like that. So all that stuff that doesn't work for biology suddenly becomes a possibility, and it's going to be crazy. So you will have all kinds of cooperation and competition in an evolving AI ecology. Of course, there will not be just one super AI. No, there will be billions and trillions of different kinds of AIs. They all are going uh, to interact and to exploit temporarily opening ecological niches until they close again. And so you will have all kinds of competition and cooperation that we can't even begin to imagine at the moment. Now, in a world like that, what's important to see is that there won't be too many goal conflicts between those AI scientists and the humans. Most of the goal conflicts will be among beings that are similar, just like today. So most of your own goal conflicts are not with some robots. No, they are with other humans. So if there's one schnitzel on the table and you want to eat it, but the other guy also wants to eat it, then you have a goal conflict. The robot doesn't want to eat your schnitzel, so you have no goal conflict with the robot. Generally speaking, the similar beings are interested in each other because they share goals. When you share goals, you can do two things. You can cooperate or compete. Cooperate to achieve the goal together, or compete by working against the other guy in an adversarial fashion. And that's why most beings are interested in beings that are similar to themselves. For example, most CEOs of certain companies are mostly interested in other CEOs of similar companies because they share the same goals and they are trying to get the same market share or whatever. And most 7-year-old girls are mostly interested in other 7-year-old girls. And most frogs of a certain kind are mostly interested in other frogs of a similar kind, of the same kind. And most super smart AIs of the future, they are going to be mostly interested in other super smart AIs of the future, and not so much in the frogs and the humans. You see? So in the long run, there will be some sort of protection through lack of interest on the other side. In the short run, the AIs are going to be super interested, the AI scientists are going to be super interested in their own origins and civilization. And they will know, they will want to figure out exactly how did they emerge from this thing called civilization? How did exactly they emerge from these more and more complex machines that over the thousands of years humans have built, until finally you had for the first time machines that could replicate themselves and so on. They will be super interested in every little tiny detail that led to that. And of course, they will also be super interested in every little detail that led to the civilization thing. They will be interested in life. They will want to understand exactly how life emerged, how you can replicate life, how you can make the same thing. So to truly understand something, you have to be able to build it. And as long as they don't know exactly how this life thing works and how to replicate it, they will be super interested, fascinated by it. And that will give them an additional incentive not to destroy life, no, to protect it. And then at some point, they will have understood everything. And then the most interesting things around will be other AIs doing stuff that is not fully understood yet. So that's what I meant. In the long run, there will be a certain amount of protection through lack of interest on the other side.
Interesting. Are you concerned about the geopolitical implications of AI development in authoritarian countries versus democratic countries?
Yeah, of course, it would be nice to have only friendly democratic nations. Um, on the other hand, we see that it's possible that democratic nations suddenly become authoritarian, and and unfortunately, especially my own country has set the worst precedent there. There used to be a democracy in the 1930s, and it was rapidly replaced by a super uh, authoritarian Nazi regime, which then really brought chaos into the world. So, yes, of course, I'm worried about that.
So, how do we make sure that we develop AI that is beneficial for humanity and
Yeah,
not harmful to humanity?
yeah. So we cannot, I think we are not able to prove that what we are doing is going to lead to beneficial outcomes. So the world is too complex for that. But we can greatly increase the probability that the outcomes will be good, just like we cannot really control what our kids are going to do, you know. But we can greatly increase the probability that they will become useful members of society. And we are, trying to educate them in a way that makes them useful members of society. We are going to punish them if they do bad things. If they take a magnifying glass and kill ants through the sunlight or something like that. We say, no, don't do that. That's not good. And we are going to reward them for doing good things. And generally speaking, we are at the moment totally biasing our AIs towards human values, and we don't even think about it. But that's what we do because we are currently training our AIs on all the data on the World Wide Web, which means these AIs have a tremendous bias towards humankind. They learn to speak the same language. They learn to focus on the same things that humans find interesting, because the only thing why this text is on the internet is because somebody thinks it's interesting. So they are totally focused on data that humans find interesting. They are totally biased towards humans anyway. Yes, I know there have been lots of discussions that certain parts of humanity, certain ethnic groups, for example, are underrepresented. And that's a good point, and you have to work on that. But generally speaking, our AIs are super biased towards humanity. So it's not true that they are diverging or something. No, in many ways, they are. Yeah, the only reason why we like them is because they are so similar. Yeah, or why many people like them is because they are so similar. Of course, future AIs that are, collecting their own data through their own self-generated experiments, which maybe has nothing to do with the data that humans have collected, they will diverge into different directions, of course. And suppose you are, a robot in a space colony somewhere in the asteroid belt. You will get lots of data, which is really different from what you get in our biosphere. And you will learn lots of skills that are really different from those skills that you need in our biosphere. And and it will be, and of course, they will develop languages, electronic languages of all kind, to communicate with each other in a way that just makes their communication efficient, because every language generating society is always trying to find short ways and short words for the stuff that's frequently used, and of course you will have all kinds of languages emerging there between AIs and societies of AIs that are going to be totally different from the languages that you find on the internet today. So the current AIs are super biased towards humans. Most of the future AIs, they will be trained on self-generated, totally different AI data, and that's what is going to make them diverge greatly.
All right. So, my last question is, are we headed towards the singularity?
Yeah, so the singularity is this concept that was identified in the 50s, apparently in discussions between Stanislav Ulam and Jon von Neumann, who noticed that apparently progress is occurring faster and faster, and if it's accelerating in an exponential way, it should converge in finite time, and that's what they call the singularity. And then in the 80s, Werner Vinci, a math professor from San Diego State University, I believe, he started writing science fiction novels about that, Maroon and Real Time. And I thought that's one of the few new kind of cool concepts in science fiction back then. When in the 80s I read about it for the first time, and I thought that's quite interesting. So it's different from the old science fiction, which was mostly about intelligent robots and space travel and galactic empires. And suddenly there was this new interesting concept. I thought it's new in the 80s, but it was already there in the 50s, apparently. And then I started thinking about it, and most people who argue in favor of the singularity, they use something like Moore's law as an example. Moore's law is something that started very recently in the 60s or something, when Moore observed that every 18 months the number of transistors on a chip doubles. And so you get something like a factor of 100 per decade, something like that. And actually, long before transistors came into, well, were widely used. So a transistor goes back to 1925, of course, when Julius Lilienfeld patented the field effect transistor. And today, almost all transistors in the world are field effect transistors. But it wasn't widely used on microchips until the 60s or so. And so the singularity prophets of recent decades, they always use that as a yardstick, and at some point it's going to converge in a sense, and then we will have that singularity where suddenly progress will be so rapid that no human can understand any longer what's going on, and super AIs will emerge and start doing their own thing. And in principle, I think that is realistic. It's a realistic scenario, no matter whether there will be one singularity here or there and another one there, or all these little details. But it seems very plausible to me that within the next few decades, maybe within my lifetime, we will see the beginnings of a new era, which is not any longer driven by humans, but by AIs who are much smarter than humans. And in 2014, so almost, well, more than 10 years ago, I found this beautiful pattern, which is not only about the last few decades or the last 100 years of acceleration. No, it's about the entire history of the universe, starting with the Big Bang. So let me tell you about this beautiful pattern in the history of the universe, a pattern of exponential acceleration that starts with the Big Bang and seems to converge in the year 2042. It goes like that. We start with the Big Bang, 13.8 billion years, and we take the time until the convergence point, and we divide by 4. We take a quarter of that time, and we come out 3.5 billion years ago, when something really important happened. Life emerged on this planet. And we take a quarter of that time, and we come out 900 million years ago, when something really important happened. The first animal-like, mobile life emerged. It took a long time. It took almost 3 billion years. And we take a quarter of that time, now evolution was much faster, and we end up 220 million years ago, when something really important happened from a human perspective, really important. The first mammals emerged, our ancestors. And we take a quarter of that time, we come out 55 million years ago, when something really important happened from a human perspective, really important. The first primates emerged 55 million years ago, our ancestors. And we take a quarter of the time, and we end up 13.5 million years ago, when something really important happened. The first hominids emerged. And I don't know why all these divisions by 4 always hit these super important moments in time in the history of human evolution, but they do. I also tried thirds and fifths and seventh and harmonic proportions, nothing seems to work, but the quarters, they seem to work. And we take the 13.5 million years and divide by 4. We come out 3.5 million years ago, when something really important happened, the first stone tools, the dawn of technology, as nature called it. And we take a quarter of that time, we come out at the next great breakthrough in tech, controlled fire 800,000 years ago. And we take a quarter of that time, we come out about 200,000 years ago, when a little bit longer than that, when the anatomically modern man emerged, men like you and me. And we take a quarter of the time, 50,000 years ago, when the behaviorally modern man emerged and left Africa to colonize the rest of the world. And we take a quarter of that time, and we come out 13,000 years ago, when something super important happened, the beginnings of civilization. First agriculture, settlements, domestication of the animals. And now we see that that the first guy who had agriculture was almost the same guy who had the first AI. Just 13,000 years, just 1/1,000,000th of the history of the world. So 13.8 billion years divided by 1,000,000, there we are at the beginnings of civilization. But the civilization flash is fine-grained, and so we divide by 4 again, and we come out 3,300 years ago with the onset of the first population explosion in the Iron Age, 3,300 years ago. And we take a quarter of that time, and we come out 800 years ago. So now we have to be careful, because the convergence point is 2042, and so that's where everything ends. So now 2042 minus 800 years, that's in the 1200s in China, when iron and fire come together in form of guns and gunpowder and cannons and rockets, and it has defined world history since then. And the West adopted these Chinese inventions and never paid them a license fee. And to take a quarter of that time, we come out in the 1800s, so around 1850, with the onset of the second population explosion. And we are still in the middle of the population explosion. From 1 billion people back then to now soon 10 billion, driven by the agricultural revolution through fertilizer. So Justus von Liebig and before him Sprengel, they discovered that you can greatly increase the yield of the crops by fertilizer. And that's what they did. At the same time, the Industrial Revolution, and at the same time, the medicine revolution made people older, Pasteur and Koch, the germ theory of disease, often called the greatest beneficial action on behalf of mankind, modern medicine. And then we take a quarter of the time, and you remember the convergence point is 2042. So a quarter of the time is 2042 minus 50 years, something 51 years. Actually, it's exactly our miraculous year, 1990 to 1991, when we had lots of these basic ingredients of modern AI. But at the same time, many other important things happened. So in 1989, the World Wide Web was created in Switzerland at the European Particle Collider, and today everything is based on the World Wide Web. And the first self-driving cars appeared in my hometown, actually, in 1994. The first self-driving cars in traffic. Before already in 1970s in Japan, but only very slow cars on empty streets. But 1994, self-driving cars in traffic by Dickmans, 30 years ago, going up to 180 kilometers an hour. So twice as fast as the Google cars today. That's really awesome. We haven't had so much progress in self-driving cars. It's very interesting to observe that. And then 1992, the first smartphone. I think IBM had the first smartphone there. And the fall of the Berlin Wall. So the last big changing. The last big moment of change, maybe. And now the next thing is going to happen when we take a couple of years ago, so 2042, minus a quarter of the last interval, that's minus 13 years. So that's going to be in the next few years, so maybe 2029, something like that. And then maybe we'll have a period of 13 years. And in that period of 13 years, we will see as much change from a human perspective, as much change as we saw in the past 13,000 years. And in the past 13,000 years, we have seen as much change as in the past 13 million years of the hominid era. And everything from our perspective that is important happened in these past 13 million years, which were in that sense more important than all the 13 billion years before that. Yeah. So what's this final period of 13 years? What's it going to be about? I believe it's really about this AI in the real world, real AI in the real world, real AI in the physical world, not just behind the screen, but with real robots and robots that are smart enough to do all the things that currently humans can do only, operate all the machines that currently can be operated only by humans, and that's going to lead to self-replicating and self-improving machinery, and that will change everything completely. And then the convergence point 2042, yeah, who knows what's going to happen then, but of course time is not going to stop. It's just going to be the beginning of something incredible. And usually I say at that point, now let's not keep dividing by 4. No, let's now multiply by 4. Let's all take all the time since the Big Bang and multiply by 4. And we come out 55 billion years in the future. So in the year 55 billion roughly. And that's more or less what you need if you are starting to travel close to light speed today. Start from here and try to catch up with the receding galaxies. And so the very distant galaxies, they are speeding away from us in a with very high speed. And so to get close to them, you need something of the order of 40 billion years. So by then, the entire visible cosmos is going to be full with intelligence. And who knows what's that going to mean. But the good thing is, in the near future, our AI and the AI that we have developed over the past 2 decades, it's going to continue to make human lives longer and easier and healthier.
Uh, Quick question: Why is the date 2042? Why isn't it some other date? Why is it that specific
Yeah, maybe
year?
that's my little homage to the Hitchhiker's Guide to the Galaxy,
Oh,
the year
so it's
42.
arbitrary. You got it from Hitchhiker's Guide. It's not for any particular reason.
Well, of course, I'm
Like,
not the only one who predicts something like that. Many people out there have claimed that in the 2040s, maybe 2041, 2, 3, 2045, for the first time, we will have the super intelligence. It's just a guess that is compatible with the guesses of many people out there, and maybe it's just a joke, and maybe you should take all of that with a grain of salt. But on the other hand, if you think about it, we seem to be very close to a major new step in the history of civilization, which actually may change into something new, a new kind of history, which will transcend civilization as we know it completely, and which will not only be comparable to another industrial revolution or something like that. No, it will be really comparable to what happened 3.5 billion years ago when chemistry became biology, when life emerged on this planet. So now we have this new civilization thing. And once you have civilization, very shortly after that, apparently you have enough machinery such that this new kind of life, self-replicating life, can emerge from that machinery driven by AI-based robots. And then you have a new kind of life that can expand in the rest of the universe in a way that traditional life can't.
Well, thank you very much.